Okay, students, yesterday we were saying about the UV-Vis Spectrum analysis. So, you see here, just made some small changes, and the changes what I've done, I have just made it here. If you see that, I just noted down because I given the graph of absorbance. From there, you can calculate the transmittance also using this formula, as well as if you see, these are all just for thin films, so that's why I've added this for thin films. You need not to write the same. I'll just check over and just come to you, and then if you see down, these are set of equations that you want to do by your own. There is no other way. This lambda maximum corresponds to the peak where you will have the largest portion of transmittance, and the lambda minimum will refer to the if there is a curve something like if you see here. So if I want to zoom here, so this portion refers to lambda minimum, then this portion refers to lambda maximum. You see a sharp curve rising, right? So this portion is lambda minimum, this portion is lambda maximum. I'm telling this on the x-axis, okay, on the x-axis, but the value of the transmittance is going to be for lambda max T max, okay, that is going to be some kind of some 80 or something like that, and the lambda minimum T minimum is going to be somewhere below this value, okay. So from that you can take the values and you can plot it in the graph, I mean do it in the table, and then you will come across this T max and T max value. You can take a series of peak 5 to 6 peaks that you want, if at all, if there is something like that, and then you find the T max T minimum using the x and y axis, and then you find the graph, I mean refractive index formula using this is okay. And then coming down here, you can consider this lambda max as the, the value for the maximum lambda 1, okay. Successive lambda which is below are going to be lambda 2, and that is going to be a minimum value, okay. And the lambda 1 lambda 2 are success wavelengths of successive tms, okay, or tms, t max or t minimum. So therefore what you're going to do is you're going to take lambda 1 as the largest value here, the first value or second value, and the successive value is going to be lambda 2. And what is the t value there? You're going to take any t value. You take the t value of this, or you take the t value of this, which is going to be t1 and sorry, n1 and n2, and therefore you'll be putting this graph table. So this table comprises of that lambda 1 and lambda 2, which is one behind the other, which is here. You can take this, and then for the same thing you are going to find the refractive indexes as n1 and n2, and you fill the same here, and then you find the thickness of the thin film using this formula, okay. And this will be around in terms of micrometer, that's why I have added mu m. And if you go down you can find the absorption coefficient using the formula, something like this, and where a refers to the absorbance, okay, where a refers to the absorbance, the absorbance can be also found, and this t refers to the average value that you put here, okay, this t. And a refers to the absorbance, and the absorbance can be found using the same this equation. uh, I mean, how do you take the absorbance from transmittance? If at all they give transmittance, okay, if they give absorbance you can do it directly. If at all they give transmittance, you can get it, I mean the absorption can be taken as e power transmission, a negative value of e power, because this, when you are taking e power on both sides, this log will get cancelled, and therefore absorbance is going to be the negative value of e power something, okay, e power transmittance. So that you are going to record. Now I have changed a small thing here. I change this value as b, where b is going to be something around 0.2. This is a theoretical value, or the model that has been proposed over the years, okay. It's not been valid validated all over the years, because this is just a model and giving is constant. Okay, as well as this is a linear equation. This is a linear equation derived from the Beer law. I mean, where the same has been found out using a linear fit. What is the best fit for the curve? They have analyzed using a linear fit model, where the linear fit can be given in terms of a linearly independent, sorry, linearly dependent equation, something like this. So therefore, using this relation, you can actually find the band gap. I have made certain changes here also. You can see on the red side. um, these are all can be used in the normal table. If you have done, that's not an issue, but it's very easy to go over this. Okay, so you have lambda here, you have transmittance here, you have absorbance from the below equation, and then you have the coefficient of this thing, where a refers to the absorption, okay, t refers to the thickness of the thin film, and this is going to be a single number, and a is going to change, and therefore all the values of absorption coefficient are going to be got by us. And you can directly calculate the value of this, because HC is going to be 1204, and from there you can calculate this value. And from this value, if you want to take the graph between this and this, then you will get a graph something like this. This is called as tau plot, TAUC, tau plot. And this equation is called as Moss relation. Okay, um, so this is how the things are going on. And you can also find this k extinction value from this graph. Okay, since you have the alpha, you have the alpha, and you have the lambda. Using the same, you can calculate the extinction coefficient. But the graphs that you should draw is going to be transmittance wavelength graph, absorption wavelength graph, okay, and essentially the tau plot that you are going to do. So that's it for this experiment. uh, that is what you're going to do. If you have any doubts, you can ask me tomorrow. Okay, thank you so much.